She was one who developed among the first three-dimensional models of the Earth's atmosphere for the purpose of studying climate. She has won many honors for this work. She was inducted in the National Academy of Sciences in 2001. She won NASA's Exceptional Scientific Achievement Medal. She was one of the Scientific American's 50 most influential scientists. Perhaps signal in this, and certainly the only one in the lectures we've had so far, she was written about in the series Women's Adventures in Science, produced by the National Academy of Sciences. This is a series targeted at young girls that detail the awe-inspiring journeys of female scientists. Perhaps various things came as a result of that. One of the reviews called her a forecaster of our future. I think that's a fair statement. Perhaps as a result of that book, she was voted Scientist of the Month by a second-grade class. So there's real fame. In any case, I'm very happy to present Inez Fung.
So I've been working on climate for a long time, and I think that it's fair to say that there are days I'm very nervous because the climate is happening the way we predicted, I'm going to say 25 years ago. The weather's getting more extreme and all the things that, the physics, the mathematics, all of that is there. But what has been frustrating for me is that we're not doing anything about it. And so that really stopped me in my tracks and say, yes, it is fun to be the nerd in the office, okay, staring at my computer, but sometime I have to face the fact that what I'm doing has implications and larger implications, and what do we do about it? So I started on a new direction, and so verifying climate treaties. And I'll tell you why I'm doing that. So before I start, what I'm doing is a large team. Some of them are here. And I just want to point out, I think that there are 4 men in that team. Ron Cohen, David Holstis, Rob Harley, and Brian McDonald. But what we're doing is to figure out how do we verify climate treaties. And all of you know about Kyoto and all of that. So you all know CO2 has been increasing. So this is the Mauna Loa CO2 record. When I started, CO2 was about, when I started working on the problem around here, CO2 was about 340 parts per million, and now it's gone to 400. Okay, when I started, before this, I started before 1990, so now you can see the fossil fuel emission has grown. Here's the 2008 economic crash, and here we go, gangbusters again. So even from 1990 to now, the CO2, the emission, emission from fossil fuel combustion and from cement emission has increased by 58%. So this is while we've been talking, okay? The emissions have been going on. So what do we do about it? The first thing is, how do we know these numbers? Okay, these fossil fuel emission numbers, CO2 emission, you know, you can go to Mauna Loa, you can go out and you can see the instruments, you can see the flasks, etc. Okay, but how do we know the fossil fuel emission? It turns out that it's based on self-reporting. The United Nations sends out a report to all the countries and say, please fill out this form. Okay, and some countries do a very good job about it. Some countries do not have the capacity to take inventory, and some countries don't know how to do it at all. Some countries say none of your business. Okay, but even so, it's a very good, to lowest order, it's a fairly good estimate, because we have C14 and we have other measures to constrain this number. So, in the US, we have 2 ways two ways of estimating the emission. The Department of Energy goes at the supply side, so this is a coal train. They weigh, you know the fuel weight, you know the combustion, you know how fine the coal particles are crushed, you know the caloric content of the coal, you know the grade of coal, and so you can convert the caloric content and the combustion efficiency into an emission factor. So you multiply. Okay, the EPA does it on the other end, on the consumption side. So the EPA does it by sector, by the agricultural sector, by the industrial sector, by transportation, etc. And so basically you have the activity, for example, steel production, and then you say how much CO2 is emitted per ton of steel produced. Okay, so it's pretty good. In the US, we agree to about 3%. So not for the rest of the world. So when we come to climate treaties, I don't need to go through the United Nations as the Framework Convention of Climate Change. I've participated in the Intergovernmental Panel for Climate Change, and that is where the scientists talk to one another. And then the other side is the Conference of Parties, where scientists go as advice or we observe. And so the Conference of Parties, you can see the COP3, COP18, etc. A lot of goodwill, a lot of conversation, a lot of diplomatic conversation, but there's not much action. So now we come there's more action at the state and local level, and so this is very recent, and you all know about California cap and trade. And so here we have signed a Clean Energy Pact with Oregon and Washington and with British Columbia. And so this is very recent. And so what you see here is a non-binding pact, emphasis on non-binding, okay? So this is being a Boy Scout, I promise to be good, okay? So what do we do about this? This is a very frustrating thing for us, and for me, I lose a lot of sleep when I read about fires here and floods over there. We have to do something soon. And so here's the EPA cap and trade. Again, this is the California electronic greenhouse gas reporting tool. Again, you have a calculating. It's a spreadsheet. It's the same thing. You have emission factors, what is your activity, and here's the emission factor, and you do a multiplication. So, like speed limit, voluntary action is good. Everyone means well. But what we must do is trust, but verify. Okay, so what we've been talking about and what got us here, what got me to where I am, is we are lacking a radar gun, okay, for climate treaties. So how do we verify, not just say, here's a spreadsheet, okay, indirect measures, and how do we actually say that the emission that somebody said is actually the amount? We've had a lot of experience with the ozone hole, and so that's where there's the Montreal Protocol. Countries agree to reduction of CFCs, and it is the atmospheric measurements of CFCs in the atmosphere that actually says, have we actually succeeded in the reduction? So here we are trying to say, how do we look at CO2? So what we need are the MRVs, the measurable, reportable, and verifiable. So what is measurable, and in particular for here, what is verifiable? And for me, what we need to verify are the emissions, and not just did you fill out the right form, did you use the right number, did you use the right spreadsheet? Okay, so here, my background is in atmospheric science. I've been looking at the CO2 cycle. So the idea is very simple. Here is a piece of land, and there's fossil fuel emission, and the wind is blowing in this direction. So if I have a CO2 sampler here and another one there, then I would expect the CO2 to be higher downwind of the emission than upwind, okay? So I know the weather, how the wind is blowing, and so if I have the right measurements, I can figure out, if I have the right measurements, I can figure out how much is coming out from the surface. So this is complementary to what I just showed you, the bottom-up multiplying spreadsheets, weighing coal and multiplying by emission factors or how much the activity, the steel production. So those are bottom-up estimates. And then what we're talking about today are the top-down inversions. So this is the inverse problem. Okay, so we measure the CO2 and then back out what the emissions are. Okay, so the two have to agree. Okay, where they don't agree, either our models are wrong or the observations, or somebody is not reporting the right emissions. Okay, so this is where we see concordance, but we're also looking for discrepancies. So to have the top-down approach, what I need are CO2 measurements, direct CO2 measurements. And so we have been trying to deploy a CO2 satellite. We have one now that was not designed for CO2, but we've been trying for a CO2 satellite. And we try to establish new local atmospheric CO2 stations, and then combine them with the models, and so then back out what the emissions are. So if I know what the CO2 is, the distribution, where it is high, where it is low, then I can figure out how the wind is blowing, then I can figure out what came out from the bottom. Okay? So this is math, not on the test, so there's a review. Okay, so the review first is variance. I think most of you know what variance is. Suppose this is the mean temperature, November temperature. Okay, so you take all the days, all the years we have temperature, and so this is the distribution, the probability that the temperature is some range. So this is the variance, and so when the variance is small, or the square root of the variance is the standard deviation. When the standard deviation is small, that means everything is tight, there's not much variation. When the variance is large, it's a messy problem. Okay, it's a messy thing, everything is all over the place. Okay. Next problem not on the test is the covariance. Now I have two variables, right, x and y, and here I have chosen x to be fossil fuel emission and y to be the difference between the CO2 at Mauna Loa, Hawaii, and the South Pole. The air mixes, it takes about 1 year for air to exchange between the northern hemisphere and southern hemisphere. So we're emitting 96% of the fossil fuel emission is in the northern hemisphere. So here we start, and it's emitting, so we're putting CO2 into the northern hemisphere, and then it's slowly going to the southern hemisphere. And so because we're emitting so fast, they never catch up. Okay, so what we have is we look at the difference between Mauna Loa and South Pole, the interhemispheric gradient in CO2, and we look at the fossil fuel emission, and so there's a very nice relationship. Okay, so you can see here we did variance, and so here the covariance is basically is how related they are. I don't need to go over that. So here, then one can fit a line, obviously a straight line through this, and so we can get the slope of the line from the covariance and the variance, and that's the regression coefficient, and we can also get the correlation coefficient. So the correlation, obviously, when the correlation coefficient is 1, they're perfectly related. When 0, they're not. Okay, when it's small, they're not very well related. Okay, you all know this. I'm just going. So the key point, not on the test, is that given I have two variables, x and y, the covariance or the R squared tells me how related they are, and I can fit a line, and so that the relationship that tells me the relationship between the two. And I have to I deliberately put in that doesn't mean causality, because if you go through textbooks, x could be murder in Manhattan and in the summer, and y could be ice cream sales in Manhattan. Okay, obviously ice cream sales are not related. Okay, it's not, one does not cause the other, but they all both happen in the summer. Okay, when the temperature is high. So this is we're not doing causality, this relationship, even though the example I showed you implied was the fossil fuel emission did cause the difference between the hemispheres. So once I have the regression, I can predict y from x, or I can infer x from y. Okay? So now we're going to go into the top-down estimates. So the first thing I'm going to talk about are global carbon data assimilation. What do I mean by that? So at some time t0, I have a whole pile of estimates of the CO2 and the atmosphere, the wind and temperature and everything of the atmosphere. And I have a model so I can make an ensemble forecast. So 6-hour forecast, you're familiar with weather forecasts. Okay, 6 hours is a pretty good forecast. Okay, so then we not only forecast weather, but we also forecast the CO2 with the weather. So then we have observations at the new time, and so then what we do is to find the best fit between what the physics, what the model projects, and what the observations are. And then we do it again. So what we're trying to do in all of this data, the carbon data assimilation, is to combine the information from an imperfect model, because they really, even today's computers, I cannot resolve clouds in the computers, I cannot do turbulence, there's things that we cannot do very well. Okay, so then there's imperfect models, and we have incomplete observations, because we don't have observations everywhere that I need, not over the oceans. So what we get is the best estimate of the weather, of the wind, of the temperature, of the CO2. And once I have the whole atmosphere, then I know what I said before. If I know the CO2, if I know the wind, I know how much is coming out at the bottom, okay, as the residual. So here is CO2 again. Here are the CO2 observations. We call this the flying carpet. Okay, so obviously this is from the North Pole here to the South Pole, and this is time, and this is the color tells you the CO2 concentration. So what we see, obviously, is CO2 is increasing in the atmosphere. In the northern hemisphere, there is a very distinct seasonal cycle, right? It's higher, first it's higher in the northern hemisphere than in the southern hemisphere. The north-south gradient, you know, what we did before, it's about 1%. Now it's 400 parts per million. It's now the north-south gradient is about 4 parts per million. The mixing time within the latitude is about 2 weeks. Okay, within the hemisphere is about 3 months, and then it's 1 year across to the other hemisphere. So what we also see here is very regular breathing of the biosphere. So CO2 goes down. So the peak here is about May, so the northern hemisphere growing season. Photosynthesis removes the CO2 from the atmosphere, and then decomposition returns the CO2. So bottoms out around October, and then the decomposition returns the CO2. It's a very regular breathing of the northern hemisphere biosphere. So in the southern hemisphere, it's about 6 months out of phase. So this is marvelous, so I can use this data. Except that the data are from a very sparse network. Those are deliberately large dots, okay? There's nothing on this map. So basically, we have several types of observations. I showed you Mauna Loa CO2. You're all familiar with Mauna Loa CO2. So there are 4 stations. We have 4 stations. One is Point Barrow, Alaska. One is Mauna Loa, Hawaii, American Samoa, and South Pole, where there are people at the station throughout the years. The CO2 is drawn in through the ceiling, and then it's dried, okay, and then it's dried, and so then it's analyzed, infrared analyzer for the CO2 amount. So you get a CO2 observation maybe every hour. But the rest of these are what we call cooperative network. So there's a flask, a stainless steel flask. It's evacuated in the laboratory, and this is in Boulder, Colorado. And so they shipped out, there are 3 sets of them, one out there at the station, one under analysis in Boulder, Colorado, and one in transit. Okay, so the instructions are go out, hold your breath, okay, release the valve. Not just that, but when the winds come from the clean air sector, i.e. from the ocean, go out and release the valve, okay? So you do it every other week. We get data approximately bi-weekly, okay, 2 flasks so that you have a replicate. So this is totally inadequate. But also, you note that most of the sites are out there in remote marine locations, and we take data when the air is blowing from the ocean. So that is because here, when we measure CO2, when I look at this, the amplitude at Mauna Loa is about 6 parts per million, okay, from top to bottom. The oscillation at Point Barrow is about 15 parts per million. If I go out here and measure, the diurnal cycle could be 50 because there are plants doing things, okay? The plants take up CO2 in the day and really, okay, and they don't do it at night, okay? So there's a large variability over land. So by design, the network is located in remote marine locations. Now we have a few more towers, communication towers, some aircraft data. This is ships of opportunity you can see here. So that's not very adequate if we're trying to infer CO2 from countries. Okay, so what we have is a CO2 from Ayres as a satellite that was not designed for CO2 but designed for temperature and water vapor and other things in the atmosphere. So here you can see how much the satellite path as the Earth rotates underneath the satellite. So we have about 2,000 observations in 6 hours, which is really much better than this method where we get 100 observations, okay? So, but unfortunately, the Ayres satellite peaks, it senses mainly the CO2 in the middle troposphere. So what do? We also have weather data. And now here you're familiar with, so this is the wind and the surface pressure, just an example. So here I have 10 to the 6 observations every 6 hours. Now I'm in business, okay? So the thing is, how do I use the weather data to inform the CO2 and then get at the fluxes? So what I have is a model, the climate model, and in the last century I put in the entire carbon cycle into the climate model. I grew trees, I dropped leaves, had chemistry in the ocean and the biology in the ocean, the whole bit. Okay, so what we have then is the climate. So we have fossil fuel emission, we have all the trees, all the biosphere, terrestrial biosphere doing its thing, and then CO2 gas exchange between the atmosphere and the ocean. So we carry CO2 in this model, but now it's a tracer, and so this is what I have is the first guess of the fluxes. So this model has 360,000 grid boxes, and every time step it outputs 55 megabytes, and I'm only saving things every 6 hours. So basically what we have is I run 64, when I do this, 64 go together, 6 hours, okay? Then we do all that. So I'll so at every time step, so if I forecast 6 hours, I haven't seen any observations yet. So at every grid box, I calculate the mean. I have 64 of these going together. Okay, so then I calculate the mean, the ensemble mean, and the departure from the ensemble mean. And so now I calculate the covariance, okay, among all the variables from between wind and temperature, between wind and CO2, and between wind and CO2 fluxes, etc. Okay, so this is the covariance, the first step. If you look at this figure, lower figure, so now I just look at the variance, okay, the red boxes. So this is just the wind and then temperature, etc. How wide, okay, that Gaussian, that bell shape, the bell curve is. So if you look at this, if I look at this, this is the 500. This is, let's say, pressure at halfway up the atmosphere. So here, where the trajectory. So this is just a few ensemble members, okay, not the 64, but some of them, where they look like raw spaghetti. Okay, things are tight. Okay, the standard deviation or the variance is small. Okay, not much is happening in the atmosphere. Where it looks like cooked spaghetti out here. Okay, the variance is large, okay? Storms are there, okay? So this is where we have instabilities, and this is in the weather forecast, and my collaborator, Eugenia Kalne, who was in charge of the research for the US Weather Service, and so what she did when she was in charge was the variance in this, where it's large, she was forecasting the error in the forecast. Okay, not just the forecast. What you get is the mean of all the ensemble members, but what you don't know is that we forecast the error in the forecast. So, but what we hear is the regression is I'm actually looking not at the red boxes, but at the blue boxes. So I see the relationship between the covariance, I see relationship between U and the wind and CO2. So if I have weather, and this is the whole thing, right? I've got 10 to the 6 weather observations every 6 hours. So where I have weather observations, I use the physics, the relationship that we develop, the regression between wind and CO2, and then I can get CO2, okay? I can say this would be the CO2 I would expect given the wind, okay, in the 6 hours. So this is how I can fill in the atmosphere, okay, where I have CO2, where I have wind, weather data, I can fill in with CO2 data. So you can see CO2 weather like this, for example. So you can, so what we have then, going back to here, is that we have the forecast. So then this is the ensemble. We make a 6-hour forecast. And so this is where I carry at every box, at every one of those 360,000 boxes. At every one, you do the covariance matrix. Okay? And then when we pull in the observations, then we do the regression to fill in the CO2. Where I have weather data, I pull in so I use the regression to get me CO2. Okay, so then we do now the least squares fit, okay, the optimal fit. So here, the forecast, X is forecast, Y is the observation, and so then I find the best fit. Okay, so I fill in the whole atmosphere. So now, and then I go forward again. So now I have the whole CO2 in the atmosphere, and I have the wind in the atmosphere, so as a residual, I can figure out what is coming out at the bottom. Okay, so this, so the satellite that the AIRS was not designed for CO2. Okay, so here is one that was designed, and look at the name, Orbiting Carbon Observatory. Somebody asked me, how did you think of it? I didn't think of it, but isn't it a nice OCO, right? There's the CO2, okay, you see the OCO? Okay, so this is marvelous. It was designed for CO2, so you have the weak absorption band. This is very narrow band, just CO2 band, 1.61 micron, and then the weak, strong absorption band. So basically, this is sunlight. You know how much sun is coming in. And so you measure at that particular wavelength only CO2 absorbed, so you know by the difference between what goes in, what goes out, how much CO2 there is in the column. Okay, but how big is the column? We have to measure oxygen. So here's the oxygen A band. We measure how much oxygen, so whether the satellite's looking straight down or looking sideways or looking some other way. Okay, but what is really cool to me is that each pixel is about 3 square kilometers. So every observation is 8 of these across. So the data rate is 3 hertz, so I get 3 of these. Okay, 3 strips of noodle, okay? And the satellite's going at 7 kilometers per second. So every second, there is 7 kilometers, okay? It goes 7 kilometers, and it's 10 kilometers this way. And I've got 24 pixels, 24 observations. This is really cool, okay? And it is deliberately small, just in case the clouds are there. Maybe we can see through clouds. Okay, so this is, and there's a calibration. Paul Weinberg at Caltech has the same instrument in a trailer, so when the satellite goes overhead, so the Paul's instrument will look up and the satellite's looking down, so you can do the calibration. Okay, so it's a marvelous thing. Unfortunately, I still have difficulty looking at this. Okay, so It didn't separate from the launch vehicle. It should have gone up and not this way. This is not what you want to see. It should have gone up. So we worked hard to have it approved for reflight, and the argument is for climate treaty verification. So it's been approved, and we're hoping for a launch in 2014. Okay, so meanwhile, we can do a simulation experiment, and so here is showing you that this is the true flux, and so when we go through all the steps that I went through, the ensemble Kalman filter, but basically it's covariance and regressions, okay? Then you can see that what we get we're really pleased, okay? So it's really good. Okay, so this is in the prototype. We think we've got a system that's working, that we can get the CO2 fluxes once the satellite's flying. Okay, so this is very exciting for me because the satellite and the system, we can get CO2 at the subnational level. And so depending on the computing power, if we have data at 3 kilometer resolution, we're not going to run the model at 3 kilometer resolution. Now the highest resolution may be 25 kilometer, maybe 100, but 25 kilometers. So we can actually do this, okay, to get the fluxes at the surface. So the data, the NASA data, freely available to the world, and our system, when it's working, we will put it on the web, and other people will download it, and they will modify it and tailor it to their own purpose. So that's fine. But a lot of, as I said, the action for climate is at the state and local level. And so one thing that we've been trying to do is to do local traffic emissions. And I see Jumi here, and this is her work. So at the University of Utah, this is Jim Ehringer here, they set up many CO2 observing sites, and this is no longer this kind of, flasks and stuff. Okay, so this is really fancy. Each instrument's about $100,000. The CO2 satellite is $300 million. Okay, that whole thing for the reflight. Here we're talking about $100,000 for the instrument. We're not talking about people. So $100,000 for each instrument. And so they have been measuring CO2 at Salt Lake City, at several sites around Salt Lake City for several years. So what Jumi did, she's there, is to look. Now we have the CO2 from the observations, okay? And then you have the traffic. We downloaded the traffic data by day from the state of Utah. And then we have other stationary estimates, the other emissions from stationary sources. So at the downtown site, there is not much. You see, there is not much vegetation. We don't have to worry about the photosynthesis and decomposition as much, and not the ocean, obviously. So this is the emission coefficient, right? Remember, so this is the M, okay? So we take the CO2, the data, calculate the time change, and then we have the traffic data and the other sources, so we calculate the emission coefficient. So don't worry about the units, it's very long-winded thing. So, but what she found is that, this is November 2008, is that on the weekend, the emission coefficient is lower than that on the weekday, and on Thanksgiving, this is November, it's much higher. So what do you think is going on? No, this is downtown. So you're driving totally differently on Thanksgiving, and this includes the Wednesday before Thanksgiving, okay, than the weekend. Okay, so here the driving, so this is how you drive. It's not just a typical coefficient for a particular type of car, but the driving conditions make a lot of difference, okay? And when she splits the weekday here, in the morning rush hour here, evening rush hour, and the rest of the day, you can see the difference. You know this, right? You know your gas mileage changes, depends on what the traffic is. Okay, but here we can estimate, we measure CO2 in the atmosphere, and she actually managed to get out the different driving conditions from the data. So this is very exciting to me, okay, that we can, this is a mobile, this is a major source of CO2 to the atmosphere, and we can figure out what is going on here. The important thing here to note is that the traffic emission varies with the driving conditions, and if you just look at these, there's a factor of 4 difference between morning rush hour and the rest of the day, when easy driving versus stuck in traffic, okay? So it's a factor of 4 difference, and this is one thing that we immediately say, if we switch our cars to electric vehicles, if we do something about traffic, you know, we can do something locally. So let's go to another example, local high density network, and this is Ron Cohen's group that's doing this. This is Jill Tiger, who, this is her PhD thesis with Ron Cohen. So here around Berkeley, around Oakland, they have put in these sensors, okay, in schools. So each one now costs about $4,000, okay, down from $100,000 per, okay, this is $4,000, and this is done with school children. So, so what we have then is for Alameda County, here's the transportation source, the emission from Alameda, so transportation here is 53%, okay? So we're going after traffic. So the beacon, so the Berkeley Atmospheric Carbon Observation Network is at Chabot, that's our clean site up the top of the hill. And then at all these other schools at the Port of Oakland, etc. Okay? So this is really cool. So you can see this Skyline High School. You can see June 15th. Okay, you can, if I break it out, you can see at Skyline High School, there's the morning when the parents idle their cars. The CO2 is very high, okay, etc. You can see the traffic pattern, but you can see summer break, okay, when the CO2 went down. But also because Skyline is near trees, okay, so you can see as the summer progresses, there's photosynthesis removing CO2 from the atmosphere, okay? So, last thing I want to show is the mobile monitoring. And so in the same way that when I showed you, we have Mauna Loa, we have South Pole globally, and then we have satellites that go around. Here what we're thinking about for local is that we have those boxes, okay, that we can deploy at schools or wherever we can deploy them. But also now we have a mobile network. So what we're thinking about is these are simple things. We're now renting them for about $300 a month. One of these gadgets, the Lycor instrument, and put them up. So here is Richmond. So here is the highway, and so here is so this is a repeated. Okay, so this is Holly drove around, okay, and so repeated. The point is to show that here is very high on the highway, and these roads, when she goes around and around, the measurements are repeatable, okay. So what Holly did when she got the whole thing working, about I think 11:30 or midnight, they went for a drive, so from her place, and so here is a path from her house down. Okay, so what she did is down to the freeway. Okay, and then here is the UC Berkeley, the cogeneration plant, and you can see the higher CO2 here. Okay, and then she went up to Grizzly Peak, and so followed a car, so higher CO2 as she went up the hill. And so then she turned around. Here's the self-plume into her own plume. Okay, so here is the self-plume. And then come down Marine, stop signs, da-da-da-da. Okay, here are the stop signs. Okay, and then went into the garage. 900 enclosed garage, 900 ppm. Okay, but what I'm trying to say here is this is, to us, is very exciting, that for local, where the action is, we are developing the system to actually make the measurement, to have these on cars. We have a proposal to put it on LBL buses. Okay, the advantage of buses is that they park at the same parking lot at night. So there's calibration of all the sensors, okay? And also when they pass one another, then I have a sense of what the variability of the air, of the CO2 in the air, right? She drove around Richmond and said it's repeatable, but I want to see if when the buses pass each other, what is the variability? So this is one of the issues when we have satellites. My model grid box is that big and it's like a pinpoint. I don't know. They tell me the retrieval error, but that doesn't tell me the variability of CO2 in my model grid box. So here we are hoping to have the mobile monitoring, but I think that the instrumentation is there, the science is mature. In the last several years, we have deployed at the Angelo Coast Range Reserve, sensors similar, not for CO2, CO2 also, but they can be powered by solar panels and cell phone communication, so everything can be in real time, and so we can monitor all of this. So the outlook, so what we see is that for one instrument, 1 hour, we can cover 3 square kilometers. And then we can put on LBL buses, and then the dream is we can put it on AC transit. Okay, so we've figured out how many buses, etc. So the idea is that for us, for San Francisco, for Oakland, we can have our own system for monitoring. So the data will be ingested as we did for the global model. We have regional models. So in the same way we have satellites and ground stations, here we have stationary, we have these boxes in places, and then we have the buses going around. So then we can merge everything into the weather model, so we have regional weather models, okay, and do the same thing and figure out the sources. So this is where we're going. So I'll stop here. I hope I have persuaded you that the treaty and protocol verification requires direct atmospheric CO2 measurements. Cap and trade involves a lot of money. Even the satellite 300 million is not much, okay, compared to how much goes with cap and trade. So what we need is something to cross-check self-reported emissions, okay? So I hope I have shown you that the mathematics, everything, all the ensemble common filters, all that, okay, it's absolutely crucial. And what I've not talked about is all the mathematics that go into the climate models, okay, that project what temperature, what precipitation, what storms might be. So all of that, there's all the mathematics in there. So I think that I hope I have persuaded you that the prospects for global and local monitoring systems are mature and ready for deployment. And we're developing, and what we're hoping to do, not the $100,000, what we're hoping to do are low-cost systems that can be scaled up and replicated around the world so that it could go anywhere rather than requiring very PhDs and very fancy instruments. And we're hoping for something that's some system that's very mobile. So thank you very much.
Thank you. We certainly have time for a few questions if people would like to ask or get into the conversation. Yeah.
I have two. One is a really short one, and that is just carbon fluxes, the change in the carbon.
Flux is emission. Sorry, I was sloppy. Same, whatever comes up, yeah.
A bigger question is talking science
I think that I would speak for myself, that I've been working on the climate problem and we've been saying, oh, disaster, which is true, okay? And I think people get tired of that. We have to come up with actionable items and solutions, and I don't need to speak for the entire Berkeley campus, and there'll be all the things that are going on for energy efficiency, for alternative energy, even for cap and trade, and I hope not geoengineering, but so different phases of dealing with the energy problem. But also here, what we're looking at is what I showed with speed limits. Voluntary compliance is nice, but you need something which is enforceable. Okay, voluntary red and green lights is not it's disastrous. Okay, so I changed into this area because until we have something that, like the radar gun, developing the radar gun, yes, yeah. So this is where we changed direction. I mean, we expanded our scope to look at what can be done.
There's a question here first and then Dan.
Yes, good evening. My name is Charles Neal. I'm the Sustainability Manager for the Peralta Community College District. Struck by a couple of things you had to say. My first question, well, a little backstory. We just, maybe a few months ago, talked with Bay Area Air Quality Management
Yes.
District about installing monitoring stations
Yes.
on our property.
Yes.
So my first question is, with this information, do you do any collaboration?
Oh yes, I did. Ron Cohen has been working with that group.
Okay.
So, and I have one where the Cal EPA is putting in monitoring stations.
Okay.
Yeah, they're totally talking to one another.
So there should come a time in the near future when some of your findings begin to drive policy.
Oh yes, we hope so.
Okay.
We certainly hope so.
Okay, fantastic. My second question, if I may.
I think that I always come back to the medical analogy. I have body, your weight, when you go in for a checkup, it's just numbers upon numbers upon numbers upon numbers. And without numbers, I can say I want to lose weight without a scale. It's not very helpful. So what we're hoping to do is to work not just as a research, not just as PhD projects for students, but in collaboration with various agencies.
Fantastic.
Yeah.
So recently with all the fracking going on and natural gas production and it's cheap and we've been replacing some coal emissions, although we've been exporting our coal. But even within the United States, it's been claiming, or the EPA, I guess, is claiming that our emissions have gone down. But a lot of people say that methane, that
Yes.
tiny amounts leaking from natural gas production is 70 to 100 times worse than CO2. So how does methane focus into your, if we say it's going down but it's really not from a global warming point of view, how do you deal with that?
Well, I'm going to not speak for Ron, who's in chemistry and developing new instrumentation for measuring things. But each methane molecule, in terms of climate change, is worth 20 CO2 molecules.
Over 100 years?
No, yeah. But if the horizon is shorter, then methane is more powerful, more potent than CO2. So that comes back to the issue of doing something. We've been arguing that methane is money. Okay, where are the methane sources? Leaking from pipelines, from venting at the oil wells, etc. So from landfills, that's money. Okay, so whereas it's the methane sources are inadvertent sources. So methane from cattle, it's the same thing. So the animal husbandry, so let's say a large German cow emits 95 kilogram methane per head per year. They don't exercise, they are fed antibiotics, whereas an Indian, the holy cows, they're about 35. They move along, they don't have the same diet as the so there is a lot of the reduction of methane is saving money. So there is, yes, I hear you about fracking, but there's also action. We don't have the mobile sensors yet. We're developing, and so what I did talk about is Ron's group is also trying to do NOx and ozone, so these things measures temperature, humidity. So we have worked with, so that there's solar powered, all of that we can do. But methane, we're not sure we can measure on little things. Okay, it requires the fancy flasks and stuff. Yes.
So verify, but then won't there be an issue about potentially the folks who have their sources, an incentive to hack the system, and so you have to think about how to prevent that. And then on the policy angle, aren't insurance companies really at this point now sort of driving some of the
Yes.
concern because they're really looking at, they're trying to model what climate change is going to be, and they're trying to price it in terms of what they're going to be facing.
Mm-hmm.
You better repeat
All
the
of-
question. I don't know, can the people in the back hear the question? Yeah, more, okay, good enough.
So
She said yes.
the challenge is I'm looking at the problem as one of developing the technology, developing the modeling framework, developing the mathematical framework for monitoring. There will always be cheaters, okay? And I don't know how to deal with it other than to say that the reporting, and this is where, to me, the atmospheric measurement and the bottom up, it's a cross-check of the bottom up. And so if we have widespread observations, especially if the satellite is flying, we have high-res, if the satellite's flying, then we have that ongoing monitoring. And so because CO2 lives in the atmosphere for thousands of years, so even if it's the plume coming out of somewhere, I see it downwind. Okay, so that's why the CO2, the satellite is so crucial for that. So we hope that with the satellite, and also what I didn't mention is the measurement of carbon-14, because fossil fuel has no carbon-14, it's radioactive, the half-life is 85, no, the E-folding, it's 8,500 years. Okay, so it's gone. Okay, fossil fuel is about 100 million years or 300 million years. So there's no carbon-14. So you can measure the C14 in the atmosphere. We can measure C14. If you measure, my colleague Jim Randerson at UC Irvine has people ship him grasses, clip grasses, and ship him grasses, and he can measure the C14 in the grasses. So in the LA area, because there's so much fossil fuel, the grasses are depleted in C14, and you can see, okay, etc. So you can see all of that. So there are many, many ways of doing that cross-check. Loopholes, I don't know how to close them.
What about the effect of the insurance companies?
The insurance companies have been, I can't recite for you, but there's at the NOAA website, it's all the billion-dollar disasters and then the frequency of billion-dollar disasters. The insurance companies certainly understand climate change. And so they are very active about predictions and about what to do. But I do not know, since I don't know the insurance company, whether they're talking to the energy companies or whether they are investing in alternative energy or they're investing in more energy efficient systems. That I do not know. Somebody else may know here.
They would be their pricing structure would drive business behavior.
Yes, they would. Yeah, yeah. I think the lesson from Sandy in Manhattan is warning. It's not just sea level; it's a storm surge. And in the case of Sandy, we had the storm surge, the high tide, everything worked together. And so the sad thing for me is that the plans for everything happened the way we said 10 years ago, or more than 10 years ago. The plans were there. Nothing was done.